Welcome to Lesson 9 of Applied Physics. This lesson covers kinematics graphs. In this lesson, you will cover the following objectives. Learn how to interpret kinematics graphs in the study of physics. Apply the mathematical properties of vectors to additional vector-based physics problems. And understand vectors in multiple forms. Oftentimes in physics class, we use a device called a motion detector to sonically range our location from a computer data acquisition probe. The following pages are examples of real data taken from such a device and computer data analysis setup. Looking at this graph, can you give a verbal description of the motion that created it? Look at the figure and assume that you can walk back and forth along the line of action shown. The motion of the object described by the graph is as follows. Starts 2 meters away from the motion detector, moving away so that it is a total of 7 meters away from the motion detector after 3 seconds. Remains at a distance of 7 meters from the motion detector for the next 3 seconds. Starts moving toward the motion detector so that it is 1 meter from the detector after 2 more seconds. Remains at a distance of 1 meter from the motion detector for the next 4 seconds, for a total of 12 seconds. How would you move to create the graph shown? The motion of the object described by the graph is as follows. Moves with a constant velocity of positive 1.67 meters per second away from the detector for the first 3 seconds, remains at a rest for the next 3 seconds, moves with a constant velocity of negative 3 meters per second for the next 2 seconds, and remains at rest for the next 4 seconds for a total of 12 seconds. The velocity of an object is basically its speed. However, unlike speed that tells nothing about where an object is headed, the velocity also describes the direction in which the object is moving. We use a convention that velocity is positive when you are moving away from the motion detector. Velocity is negative when you are moving toward the motion detector. Velocity is the time rate of change of distance, so it can be calculated as follows, where x_o and x are the initial and final distances or positions, and t is the elapsed time. Note, the equation is correct only when the velocity does not change with time. For example, the velocity is constant or acceleration is 0. What words can you use to describe the motion in the graph shown? The motion of the object described by the graph is as follows. Moves with a constant velocity of positive 1.67 meters per second for the first 3 seconds. Remains at a rest for the next 3 seconds. Moves with a constant velocity of negative 3 meters per second for the next 2 seconds. And remains at rest for the next 4 seconds for a total of 12 seconds. This data was recorded by moving a cart in front of a motion detector on a long track, similar to the setup shown in the figure. Understanding graphs is essential in your study of kinematics. The kinematic equations stem from either the slope of the line or the area calculated under the curve. Here is a table of data which can be easily read from the graph itself. It was placed in tabular form to help you organize your thoughts. You can calculate the slope of a distance versus time graph and come up with the velocity. On your own, do so using the data and insert the answers into the final column of the chart. Here is the formula you should be using. Velocity is the time rate of change of distance, so it can be calculated as shown here. Using the formula, it is possible to calculate the velocity for the various time intervals of the experiment. Can you now plot a velocity versus time graph of the object whose distance versus time graph is given here? Each straight line segment slope is calculated for the distance versus time graph and is analyzed separately. These slopes give you the velocity for the object. The next page shows the corresponding velocity versus time graph you should be able to draw. The motion of the object described by the graph is as follows. Moves with a constant velocity of positive 1.67 meters per second for the first 3 seconds. Remains at a rest for the next 3 seconds. Moves with a constant velocity of negative 3 meters per second for the next 2 seconds. And remains at rest for the next 4 seconds for a total of 12 seconds. Let's look at a velocity graph and then the distance graph in an animation. Suppose you had to work backward, i.e. reconstruct the distance versus time graph from the velocity versus time graph. You would notice that it is not possible to figure out the initial or starting distance at time t equals 0. This means that any starting distance is allowed. In other words, there is no unique distance versus time graph from a given velocity versus time graph. However, regardless of the initial distance that you choose, you will find that the difference between the initial and final positions is the same, although not the initial and final positions themselves. This difference between the initial and final positions of the object is called displacement. Henceforth, this term will be used instead of distance to describe the motion of an object. After playing with the ideas from graphing motion as either position versus time or velocity versus time, you should be able to see where the following equations were produced. They are the results of either finding the slope, linear equation, or the quadratic function from one of these graphs. Once you compare the equations to the graph types, you should have a sure-proof method of understanding multiple ways to represent motion. You can fully describe motion in pictures, words, graphs, and also mathematical equations. The three Newton's kinematics equations are shown here, where x sub 0 x equals initial final positions, v sub 0 v equals initial final velocities, a equals acceleration, and t equals time elapsed. This notation varies slightly from the book, where they assume x sub 0 equals 0. The average velocity over a given time interval is as follows. Note, for all of the equations, the acceleration is constant. If you are given any kinematics graph, for example, velocity versus time, you can use that to determine other graphs, like distance versus time or velocity versus time, using the three kinematics equations of motion. Here's an example. Given the velocity versus time graph, you can calculate the acceleration versus time graph by using the first equation of motion. For each time interval, we can calculate the acceleration as follows. Note, if you solve this kinematic equation for acceleration, you see that the acceleration is really the difference between the initial and final velocities divided by time. This is really just a calculation of the slope of the velocity versus time graph. Hence, the slope of a velocity versus time graph allows you to calculate the acceleration. Can you make a statement about this graph? The motion of the object described by the graph is as follows. The first 3 seconds of motion, the object has 0 acceleration. For the next 2 seconds of motion, the object has -5 acceleration. For the next 2 seconds of motion, the object has 0 acceleration. For the next 3 seconds of motion, the object has +5 acceleration. And for the next 2 seconds of motion, the object has 0 acceleration. Notice that we couldn't say anything about the object's speed or velocity, or we couldn't tell where the object was located. This graph doesn't give us that information. Can we calculate the final velocity at each acceleration change for this graph? To do so, you have to assume that t equals 0, v sub 0 equals 0. Then for each time interval, we can calculate the velocity as follows. Note that the v for one time interval is used as the v sub 0 for the next time interval. Can we now calculate the positions at each velocity change from a velocity versus time graph? Again, you have to assume that t equals 0, v sub 0 equals 0, and x sub 0 equals 0. Then for each time interval, we can calculate the displacement as follows. Note that the x for one time interval is used as the x sub 0 for the next time interval. Review this image. The parabolic shape implies that an acceleration is occurring. You must always be careful to examine whether or not the displacement versus time graphs show a linear form or the parabolic shape. This example is what mathematicians call a piecewise function. You can see for the first 2 seconds a positive acceleration for the next approximately 4 seconds, a negative acceleration, and then for about 1 second a positive acceleration, followed by a constant velocity motion. Average velocity is related to the total displacement and total time as follows. For the graph, the average velocity can be calculated as follows. Note that the average velocity is also the mean of the initial, v sub 0, and final, v, velocities in the time interval. There are a number of great tools that can be used to help you understand how to make these graphs and motion seem sensible. One of them is hosted at the PHET site at the University of Colorado. Take time to go out and play with the Moving Man software. It is free and has proven to be useful to a number of students in the past. Please take the time to explore this little physics game, as it will be helpful in allowing you to understand how the moving man and his graphs are created. There are a number of great tools that can be used to help you understand how to make these graphs and motion seem sensible. One of them is housed at the Addison Wesley textbook site called Active Physics. Take some time to go out and play with the various problem set examples. It is free and has proven to be useful to a number of students in the past. If the Moving Man software wasn't sufficient enough, it is recommended to try out some of these, as they are rather interesting. Now that you understand how to describe motion in many methods, you will change your focus to applying the concepts of the mathematical tool known as the vector to also assist you in making calculations related to kinematic quantities. Follow the arrow to continue along the path into the next part of the lesson on vectors.